Far away, at the very edge of our sun's family, a deep blue world spins in the cold darkness. This is Neptune. It is a giant made of gas and ice. From Earth, it looks like a peaceful blue marble, but this quiet appearance hides a world of great mystery. Scientists look at Neptune through their powerful telescopes. They send signals across billions of miles. Yet, the more we learn about this distant giant, the more questions we find. Neptune is not behaving as we expect. It is a planet full of strange surprises and secrets that challenge everything we thought we knew about how planets work in the cold, distant regions of space. Imagine a world so far away that sunlight is 900 times weaker than it is on Earth. It takes light over 4 hours to travel from the Sun to Neptune. When NASA's Voyager 2 spacecraft flew past it in 1989, it gave us our first and only close-up look. The pictures it sent back were stunning. They showed a vibrant, active world, not a frozen, quiet one. This single visit revealed storms larger than our own planet and winds faster than the speed of sound. Neptune was supposed to be a simple, cold giant. Instead, it showed us a personality that was wild, chaotic, and deeply puzzling. The mysteries begin with its very appearance. Why is Neptune such a brilliant, deep blue? Its neighbor Uranus is made of similar materials but is a pale, hazy cyan. Something inside Neptune is creating this vivid color, something we do not fully understand. Scientists believe methane gas in its atmosphere absorbs red light, leaving the blue color to be reflected. But that alone does not explain the difference between the two ice giants. There must be another chemical, another process at work in Neptune's churning atmosphere. This color is the first clue that Neptune is a world with a complex inner life, one that we have only just begun to glimpse from afar. Every new piece of information we gather seems to add another layer to the puzzle. We see its clouds appear and disappear with the seasons, but Neptune's seasons last for 40 Earth years. We detect strange temperature changes that defy our climate models. This planet is a grand scientific enigma, a beautiful blue question mark hanging in the vastness of space. It challenges our best scientists and engineers. To solve these riddles, we must look deeper into the heart of this ice giant. We must explore its powerful winds, its strange internal heat, its tilted magnetic field, its faint rings, and its captured moon, Triton. Let us talk about the wind. Let us talk about the wind. On Earth, a powerful hurricane might have winds of 300 kilometers per hour. That is fast enough to cause massive destruction. Now, try to imagine winds on Neptune. They are the fastest winds ever recorded in our solar system. These winds scream across the planet at more than 2,000 kilometers per hour. That is faster than the speed of sound on Earth. Think about that for a moment. A storm on Neptune moves faster than a fighter jet. This is happening on a planet that receives very little energy from the sun. It is so cold and so far away, yet it powers these incredible supersonic winds. This is a huge mystery that scientists are working hard to solve. Where does the energy for these winds come from? On Earth, the sun powers our weather. It warms the oceans and the land, creating temperature differences that drive winds and storms. But Neptune is more than 30 times farther from the sun than Earth is. The sunlight that reaches it is just a faint glimmer. This tiny amount of solar energy is not nearly enough to create the monstrous winds we observe. So the power must be coming from somewhere else. The planet itself must be generating the energy needed to fuel its own violent weather. Deep inside Neptune, there may be a source of heat. An internal engine churns the atmosphere from below. When Voyager 2 flew by, it saw a huge storm called the Great Dark Spot. It was a massive, swirling vortex as big as our entire planet. It looked similar to Jupiter's Great Red Spot. But unlike Jupiter's storm, Neptune's storm was gone just a few years later when the Hubble Space Telescope looked. Since then, other dark spots have appeared and vanished on the planet. These storms are not permanent features. This tells us Neptune's atmosphere is incredibly dynamic and changes much faster than we ever thought possible for such a cold world. Understanding these winds is key to understanding Neptune itself. They are a sign of the planet's active and energetic interior. The speed, the power, the temporary nature of these storms are all clues. They hint at a complex relationship between the planet's deep core, its icy mantle, its upper atmosphere. Scientists try to create computer models to simulate these winds, but our models struggle to replicate what we see. We are missing a critical piece of the puzzle. We need to know more about the heat flowing from Neptune's core. Without that knowledge, the winds at the edge of our solar system will remain a beautiful and terrifying mystery. One of the biggest puzzles about Neptune is its internal heat. Most planets in our solar system get their warmth from the sun, but Neptune is different. It actually gives off more than twice the amount of energy it receives from the sun. This means the planet is hot on the inside. It has its own internal engine generating a tremendous amount of heat. This internal furnace likely powers the planet's supersonic winds, chaotic weather systems. Where does all this extra heat come from? Why is Neptune so hot inside when it should be cold and quiet? Scientists have a few ideas, but none fully explain it. One idea: heat left over from formation, billions of years ago. When gas and dust came together to create Neptune, the process generated a lot of heat. Maybe the planet is still slowly cooling down, releasing ancient heat into space. But the theory struggles when we compare Neptune to Uranus. Uranus is similar size and mass, yet shows almost no internal heat. It is cold, almost inert. Why would twins behave so differently? Another idea: gravitational contraction. Neptune could still be shrinking under immense gravity. Compression squeezes the core material. That squeezing generates friction and heat like a bicycle pump warming when you use it. Another possibility: heavy materials like diamonds raining through the mantle. Falling diamond raindrops release gravitational energy as heat. Sounds like sci-fi, but plausible under extreme pressure and temperature. Even so, the numbers do not fully add up. The heat coming from Neptune is still surprisingly large. Our models cannot fully account for it, especially with Uranus beside it for comparison. The contrast between these two worlds is the heart of the mystery. Neptune is warm and active. Uranus is cold and quiet. Understanding why would teach us something fundamental about giant planet formation and evolution. To solve this, we need to send a new probe to measure heat flow from Neptune's interior directly and in much greater detail. Every planet with a magnetic field has a north pole and a south pole, just like a simple bar magnet. On Earth, our magnetic field is pretty well behaved. The magnetic axis is tilted only about 11 degrees from our rotational axis, so your compass needle points roughly toward the North Pole. But on Neptune, the magnetic field is a complete mess. It is wild and chaotic. It is not generated from the center of the planet. Its axis is tilted by a staggering 47 degrees. It is almost lying on its side. Even weirder, the center of Neptune's magnetic field is far from the planet's center. It is offset by more than half the planet's radius. Imagine if Earth's magnetic North Pole was down in Mexico instead of near the geographic North Pole. Neptune rotates every 16 hours, and this tilted, offset field tumbles and cartwheels through space. That creates a complex, rapidly changing magnetosphere, the space controlled by the planet's magnetic field. It is unlike Earth, Jupiter, or Saturn. So what could cause this? Scientists point to what is inside Neptune. On Earth, our field comes from molten iron in the outer core. Ice giants are different. They lack a liquid metallic core. Instead, the field may form in a shallower layer. Deep inside, Neptune is a slushy mantle of ice. Water, ammonia, methane. Under immense pressure, that slush becomes electrically conductive. Moving, churning conductive ice could generate the magnetic field. Because that layer is closer to the surface, it helps explain the offset and tilt. When people think of rings, they usually think of Saturn. Because Saturn's rings are bright, wide and magnificent, easily visible even with a small telescope from Earth. but we now know that all 4 giant planets in our solar system have ring systems. Neptune's rings, however, are perhaps the most mysterious of them all. They are so faint and dark that they are almost impossible to see from Earth, like whispers in the dark, made of material as black as coal. Voyager 2 gave us our first clear look at them, and what we found was very strange. Unlike Saturn's broad, uniform rings, Neptune's rings are clumpy. They are not smooth, continuous bands of material. Instead, some parts are much denser than others, forming bright arcs. The main ring, named the Adam's ring, has 5 distinct arcs that are much brighter than the rest of the ring. These arcs are named Fraternité, Égalité 1, Égalité 2, Liberté, Courage. According to the laws of orbital mechanics, these clumps should spread out evenly around the entire ring in just a few years. The material should distribute itself into a uniform band, but it does not. Something is holding these arcs together. Scientists believe that the gravity of a small moon, Galatea, might be responsible. Galatea orbits just inside the Adam's ring, and its gravitational pull could be creating stable zones, or corrals, where the ring material can gather and form these arcs. This is known as a gravitational resonance. The moon's gravity essentially herds the dust particles, preventing them from spreading out. This is a clever explanation, and it seems to work in our computer models. However, the models are not perfect. The interaction between Galatea and the rings is complex, and we are not sure if its gravity alone is enough to explain the stability of all 5 arcs over long periods. Another puzzle is what the rings are made of and why they are so dark. They are likely composed of tiny dust particles, possibly mixed with ice that has been darkened by radiation over billions of years. The darkness suggests they might be rich in organic, carbon-based compounds. Where did this material come from? Perhaps it is the debris from a small moon that was shattered by a comet impact long ago, or maybe it is dust that was kicked off the surface of Neptune's inner moons by micrometeoroid impacts. The faintness and clumpiness of Neptune's rings make them a fascinating laboratory for studying how ring systems evolve. But, we need more data to test our theories and solve the mystery of their ghostly arcs. Neptune has many moons, but one of them stands out as truly bizarre: Triton. It is Neptune's largest moon, and it is one of the most fascinating objects in the entire solar system. The first strange thing about Triton is its orbit. Almost every large moon in our solar system orbits the same direction the planet spins. This is called a prograde orbit. It suggests the moon formed from the same swirling disk of gas and dust as the planet. But Triton orbits backward. It moves in the opposite direction of Neptune's rotation. This is called a retrograde orbit. This is a huge red flag for astronomers. A retrograde orbit is strong evidence that Triton did not form with Neptune. Instead, it must have been a rogue object that once orbited the Sun on its own, like Pluto does. It was likely a dwarf planet from the Kuiper Belt, the region of icy bodies beyond Neptune. At some point in the distant past, Triton must have wandered too close to Neptune and was captured. This capture event would have been a violent and chaotic process. It would have disrupted any original moons Neptune had, smashing them to bits or flinging them out of the system. The debris from this chaos might even have formed some of Neptune's current small moons and its faint rings. When Voyager 2 flew past Triton, it revealed a world that was even stranger than its orbit suggested. Triton's surface is incredibly young and active. It is one of the coldest places in the solar system, about -235 degrees Celsius. Yet, despite this extreme cold, Voyager 2 saw giant plumes of dark material erupting from its surface. These are cryovolcanoes, or ice volcanoes. They do not spew hot lava, but rather nitrogen ice, methane, dust. These plumes rise several kilometers into Triton's thin atmosphere before being carried sideways by the wind. This geological activity is shocking for such a cold body so far from the sun. It could be driven by seasonal changes. As the faint sunlight warms the surface, it could cause frozen nitrogen below the surface to turn into gas, building up pressure until it erupts violently. Another idea is that tidal forces are at play. Because of its strange decaying orbit, Triton is being constantly stretched and squeezed by Neptune's gravity. This tidal friction could be generating enough heat in its interior to power the cryovolcanoes. We have so many questions about Neptune, but getting answers is incredibly difficult. The biggest reason is simple. It is extremely far away. Neptune is about 4.5 billion kilometers from Earth. This immense distance creates a whole host of challenges for scientists. Sending a spacecraft there takes a very long time. Voyager 2, our only visitor, took 12 years to reach Neptune. A new mission might be faster, but it would still be the better part of a decade. That makes missions to Neptune expensive, complex, and very rare. With only one mission, our data is extremely limited. Voyager 2 did not orbit, it flew past. It spent only a few hours collecting detailed information, then continued out of the solar system. Imagine trying to understand all of Earth by looking at it for just one day. You would get a snapshot, but you would miss the seasons, the long-term weather patterns, and slow geological changes. That is our situation with Neptune. We have a single, precious snapshot from 1989. Everything else comes from telescopes on or near Earth. Hubble Space Telescope, James Webb Space Telescope. Even the best telescopes show Neptune as a small, distant dot. Fine surface details and faint rings are hard to see. The signals we get are faint. Communication is a huge problem. Radio signals take more than 4 hours one way from Neptune to Earth. You cannot control a spacecraft there in real time. You send a list of commands, then wait over 8 hours, 4 hours there and 4 hours back, to see if it worked. That slow loop makes exploring a dynamic world very challenging. When models fail to predict Neptune's weather, its internal heat, or its magnetic field, it shows our understanding is incomplete. So, how do we solve the many puzzles of Neptune? The answer is clear. We must go back. Scientists and engineers are already dreaming up new missions. The highest priority goal is to send an orbiter. Not just a flyby, but a spacecraft that enters orbit. It would circle Neptune for years, mapping its atmosphere, mapping its magnetic field, mapping its rings. It would watch weather change through the seasons. It would measure heat flowing from the planet's interior. An orbiter would turn a single snapshot into a feature-length film. A future mission would also carry an atmospheric probe. The probe would plunge into Neptune's clouds. It would measure temperature, pressure, chemical composition as it descends. The mission could include flybys or a small probe for Triton. A closer look at Triton's ice volcanoes and its strange surface would reveal how captured worlds evolve. While we wait, we can still make progress. The James Webb Space Telescope is already giving stunning new views of Neptune. Its infrared instruments can see through haze and peer deeper. JWST gave the clearest images of Neptune's rings since Voyager 2 and detected new cloud features. On the ground, the extremely large telescope is being built. Massive mirrors will collect faint light and resolve new details. Scientists are also improving computer models. They turn limited data into better simulations of Neptune's interior and atmosphere. By testing theories in virtual labs, they can target the most useful measurements. For example, they can model how internal heat sources affect winds. That helps design the perfect instruments for an orbiter. Neptune remains one of the last great unexplored frontiers in our solar system. It is a world of extremes, supersonic winds, mysterious heat, a moon that travels the wrong way. Every fact we learn opens a dozen new questions. It challenges our theories, pushes the limits of our imagination. This is what makes science so exciting. Unknowns drive us to explore, to innovate, to push beyond our boundaries. Neptune is a promise of future discovery, a reminder that great mysteries await. The journey will be long and difficult. It will require patience, ingenuity, global commitment to exploration. A new mission is a generational project inspiring scientists, engineers, dreamers. Children watching a Neptune launch may become the analysts years later. Long-term vision is essential for deep space. An investment in our future, an investment in knowledge and our curiosity as a species. What secrets will we uncover? The future of discovery shines with a faint, distant, beautiful blue light.